Hello guys, welcome to my YouTube channel Physics Prince. My name is Deepak. I'm going to teach you all 9 subjects of physical science in detail. My courses are absolutely free of charges. My courses are going to help the students who are preparing for CSIR, NET, GATE, NT exam, PhD exam, SET exam, IIT-Jam, Jest, TIFR and other exams related to physical science. Okay, so this is the lecture number 9th of the condensed matter physics. Okay, so in which we are going to discuss that is Bragg's condition in first in Breva zone, okay, and lattice vibration in 1D, right? So last time in last lecture my class was ended automatically because of technical errors. So I was deriving this one reciprocal lattice, right, and that is Bragg's condition uh, in uh, in Brema zone, right, and that time the class was ended automatically. So I'm going to start from there. Okay, so and also guys, before starting the class, I would request the students who haven't subscribed my channel yet, please subscribe my channel and watch my free live lectures which are going to help you to crack the exams related to physical science. Okay, so let's get started. Okay, so that is we are doing this Bragg's condition, right? We know this. I have already I was doing in my previous lecture, guys. So okay, I'm starting from that point where the from where the class was ended. Okay, so right, and this one we know that Bragg's law, right? Bragg's law. This one, Bragg's law in reciprocal lattice vector, right? In reciprocal lattice. Okay, so this one we know the Bragg's law, that is 2 into k dot g in reciprocal lattice. Okay, this is a Bragg's law in reciprocal lattice, and the first Brema zone also I have explained in last lecture. So that is k plus k dot g into g square into g square equal to 0, right? This is the Bragg's first law. This is the equation number 1, guys. So here we know that the vector g value, this I have already explained. Vector g value we know that is u vector a plus v vector b plus w vector c. These are capital letters, right? W vector c, right, where u v are integer, right? And now because we are talking about 2D, right? That I have already explained in my previous lecture. We are talking about 2D lattice. Okay, so that is we're talking about this one. Just wait, guys. Square. We are talking about square lattice. Okay, of lattice constant a, right? So for that, for square lattice for in 2D, value of g is going to be. So we are discussing about 2g, in 2D, right? So this is going to for square lattice of lattice constant a. So this is going to be u. I have already explained that in my previous lecture, guys. I would request you please check that lecture because yesterday my class was ended automatically because of technical error. So that's why I'm starting from that point. Okay, so this is going to be u vector a plus v vector b in 2 dimension. Okay, now what we are going to u v are integer. So now taken taken u and v taken u and v u and v as taken u and v as hk where hk are Miller indices, hkl are the Miller indices, right? So we have taken u and v as hk. So in that case g is going to be uh, ha plus kb. right? HA plus KB. And now value of AB, which I have already explained in my previous lecture, that is value of vector A is 2 pi upon A I cap, and value of B is 2 pi upon A J cap. I would request you, please watch my previous lecture, okay? Then you will easily understand what I'm teaching at the moment, okay? I cap, this we know. So we can put the value. So G, the value of G is going to be, then vector G, this is equation 1, okay? The vector G is going to be H into this, we can write 2 pi, right? So 2 pi, 2 pi H, 2 pi H upon A, 2 pi H upon A, that is I cap, okay? We have put the value of this, right? Plus 2 pi K upon A J cap. Vector A and vector B value are this, right? Okay, and value of vector K we know, that is Kx I cap plus Ky J cap, okay? Kx I cap plus Ky J cap, okay? So now we will put the value of G and K in equation 1, okay? I would suggest you please watch my last lecture, okay? Because that time in my last lecture yesterday, my class was ended automatically because of technical error, okay? So that's why I was doing the same thing, this thing, right? That time the class was ended, okay? So for understanding it properly, I would suggest you please watch my previous lecture. So these are the value of K and G and K, right? So now we will put value of G and K in equation 1, okay? Putting value of G and K in equation 1, okay? So if you put it, now it's a dot product, guys, right here. This is K dot G, means K dot G. This is I cap is going to be 1. So 2 pi H kx upon A plus 2 pi, this is 2 pi, this is going to be 2 pi, this one, right? So this is going to be, right? So this is 2 pi K ky upon A, right? So this is S, this is K. K is also here, guys, okay? And this K, right? So I will just put it. So this is going to be 2 into factor product. It is going to be 2 pi upon A H kx, right? We know the vector product, very simple, this product, right? So these are constant. 2 pi H upon A into kx is constant, right? And I dot I is 1. Similarly, 2 pi K upon A is constant and ky is constant, right? J dot J is 1, right? So this is going to be kx plus 2 pi K kx upon A, 2 pi K ky. This is ky, guys. My apologies. It's ky. It's ky. Okay. This one ky. Okay. So this is the one, and plus value of G square. Value of G square. G square value is this, plus 2 pi H upon A whole square plus 2 pi K upon A whole square, that is equal to 0. Okay. So this is the value of G square. Okay. Now simple calculation. So we are going to calculate it simply. Okay. So this is going to be, so 2 pi upon A, 2 pi upon A, right? And this 2 pi upon A and 2 pi upon A, these are constant, right? They will go in right hand side. So this is going to be, and 2, right? So this value is going to be, these are same value, so this will be 2, right? Okay. So this is going to be h kx plus k ky, these values will remain, right? Minus pi upon a, minus pi upon a, this is going to be h square plus h square plus k square. So this is the case of 2D, guys. Okay, this is very important relation, guys. I would suggest you please watch my previous lecture for understanding it properly. Okay, so this is called Bragg's condition for Briva zone. Okay, so this is Bragg's condition for Briva zone. Okay, this is BZ. Okay, Briva zone. In Briva zone, in short we say we can write as BZ. Okay, so this is the Bragg's condition for Briva zone. Okay, or also I have already explained Bragg's condition for reciprocal lattice, right? That was explained by me, and also I have explained Bragg's law and also Bragg's diffraction law. Okay, and also Bragg's law in reciprocal lattice, Bragg's law in direct lattice. That was already those things were already explained. Okay, so this is very important result, guys. You need to note. You need to note down. So here, the value of kx is value of kx is plus minus pi by e. Okay, and value of ky is plus minus pi by e. Okay, so now I'll make a diagram. Okay, I'll show you the first Briva zone, second Briva zone, and third Briva zone. Okay, how we represent that those Briva zones in momentum space. Okay, so here this one hk, or so this I'm representing in 2D. Okay, so that's why I'm just taking hk, not l. Okay, because we are discussing it for 2D. hk values are, because hk values are 1 0. Okay, here h values are showing, here h values are plus minus 1 and value of k are plus minus 1. Okay, so h value we can say 1 1 0 and minus 1 0, and value of k is going to be 0 1 0 minus 1, right? Because a value of h k are plus minus 1. Okay, so now I'll make a diagram. I'll make a diagram in next page. Okay, and the value of kx is this one, plus pi by a. Okay, and kx is minus pi by a. Similarly, ky is plus pi by a, and ky is minus pi by a. Okay, so I'll show you how first, second, and third Briva zone in momentum space. I am going to show you. Okay, I'll make a diagram for this. So this is going to be like this. This is momentum space, guys, kx and ky. Okay, and the first Briva zone I have already shown you yesterday. Okay, you can check my this, this is first Briva zone. Okay, this is first Briva zone. That is, this is pi by a comma 0. This coordinates, and the coordinate is minus pi by comma a 0, and this is 0 comma pi by a, the coordinate of this. Okay, and this is 0 comma minus pi by a. Okay, so this is the first Briva zone. Okay, and now next is like this. KY. Okay, so this is going to be like this. This is straight line, guys. Okay, it is not looking, consider it straight line, guys. Okay, this one. Okay, this is like this, and then this is like this. One. These are straight lines. Okay, may not look, so consider these are straight lines. Okay, okay, guys. So guys, this is the first Brima zone. Okay, and which I have like shaded. This is second Brima zone. Okay, I'll come to right. So this is second Brima zone. Okay, it's a French name, guys. Okay, so the exact pronunciation is Brima. Okay, in India we say Brilliant zone, but that's not correct. Okay, it's Brima zone. Okay, this is second Brima zone. Okay, and this is the third Brima zone, guys, in momentum space. Okay, this is the graph between kx and ky. Okay, in 2D. Second Brima zone, and this is third Brima zone. I'm going to write as bz. Okay, and what remaining? Okay, yeah, this distance is 2 pi by a comma 0. Okay, and this is minus 2 pi by a comma 0. Okay, and this is minus, my apologies, 2 minus 2 pi by a. Okay, and here this is 0 comma 2 pi by a. Okay, this is the distance, guys. Okay, and this is the third billion zone. It's third Brima zone. It's a second Brima zone, and this is the first Brima zone. Okay, first. This is very important, guys. For we can solve lots of question if you know those different Brima zones. Okay, first Brima zone. Okay, this is the one. Okay, so now we'll find area of first Brima zone, second Brima zone, and third Brima zone. Okay, okay. So I hope I'm audible, guys. Let me just check. I'm audible or not. And yes, I'm audible. So I'm going to proceed further. Well, so now we'll find the area of first Brima zone, second Brima zone, and third Brima zone, and we'll find that that area will be same. Okay, for these three Brima zones. Okay, well, so area of first Brima zone, that is, I have already explained in my previous lecture. Okay, area of first first Brima zone. Okay, that is I have explained in last, that is 2 pi upon a whole square. Okay, and if you open it, so this is going to be 4 pi square upon a square. Okay, so this is the area. This is the area of first Brima zone, right? This area. This is pi by a. So this how it is, we know, very simple. This this distance is pi by a, right? Pi by a. This distance is pi by a. This total distance is 2 pi by a. This is a square. Length is 2 pi by a, and width is 2 pi by a, right? So square area is the length into breadth, right? Breadth, right? Or length into width. So that is 2 pi a into 2 pi a, right? 2 pi a whole square, right? This is the area of first Brima zone. Second, this one. Now this is the one. Okay, this is the area of first Brima zone, and similarly the area of second Brima zone. Okay, area of this can also ask in question, guys. Okay, this can also be asked in question. So second Brima zone. Okay, second, I'm writing in short, this one. So from here, understand, guys, this one. This is see, this is pi by a, right? This distance is pi by a, right? So this distance, this total distance is 2 pi by a, right? This one is 2 pi by a, 2 pi by a. And area of triangle, we know, right? Area of triangle is 1 by 2 base into height, right? 1 by 2 base into height. Base is 2 pi by a, and the height is this is pi by a, right? So this is going to be 1 by 2 into, and there are 4 triangles, right? 1 2 3 4. So 4 into 1 by 2, 2, this base is 2 pi upon a into height is pi by a, right? So 2 will get cancelled. Okay, so this is 4 pi square upon a square, right? The same one, same as this one, 4 pi square upon a square, right? And similarly the area of third Brima zone, that is also here, right? So this total distance is, this one is 2 pi by a, right? So this is going to be 2 pi by a and 2 pi by a, right? So this is 2 pi by a into 2 pi by a. Okay, so this is the one. Only this part, right? The same thing. So this is also 2 pi by a. This is also 4 pi square a square. Okay, so the area of first Brima zone, second Brima zone, and third Brima zone is same, and this is the representation of different Brima zones in momentum space. Okay, now next is this, we can write here, area of all, we can write, right? Area of all PZ, that is Brima zone, is same in 2D. Okay, we are discussing 2D case, guys. Okay, this is very important equation, you need to note down this one. This is the Bragg's condition for Brima zone in 2D. Okay, and this is like this. Okay, and this implies the area of all Brima zone is same in 2D. And now, and similarly, the volume of, if we discuss 3D case, then volume of all Brima zone is same. This is also same in 3D. These are very important point, guys. You need to note down. Okay, and next point is first Brimah zone is reciprocal lattice itself. Okay, this I have explained yesterday. Reciprocal lattice itself. Reciprocal lattice itself. Okay, so first Brimah zone is reciprocal lattice itself. We have seen yesterday. I have explained that. Okay, so it is in 2D case. Okay, so this is about the Bragg's condition in Brimah zone, and this is the different types of Brimah zone I have explained and I have drawn in the momentum space. Okay, next is okay, this is the one. Okay, guys, so next is going to be this one. Next is there's the next chapter. Okay, I'm going to start, and that is lattice vibration, guys. Okay, lattice vibration. Lattice vibration. This is the next chapter, guys. Okay, very important chapter, lattice vibration. Lattice vibrations. Okay, so first we know the restoring force, right? Restoring force we have studied. Restoring force. Restoring force is, that is F equal to minus kx, right? This is what we know, uh, and also we know that acceleration A equal to, that is minus omega square x. Okay, x is d2x upon dt square, right? This is omega square x. This is the equation of simple harmonic motion. Okay, it's equation of simple harmonic motion, right? Where omega is the frequency and a is the acceleration. Okay, x is displacement. Okay, so now we are going to study, that is 1D monoatomic, one dimensional monoatomic lattice. Okay, one dimensional mono monoatomic lattice. One dimensional monoatomic lattice. Okay, one dimensional monoatomic lattice. So I will show you one dimensional monoatomic lattice. So this is monoatomic lattice. Okay, okay, so this is the one dimensional monoatomic lattice. Okay, and they are they looks like they are attached with spring. Okay, whose spring constant is k. Okay, they vibrate in their mean position. Okay, and it seems that they are attached with a spring. Okay, okay, and the spring constant is, let's say, c. Okay, this is the spring constant. Okay, so we'll find the frequency of the lattice vibration. Okay, so this is the lattice vibration in one dimensional. Okay, so one dimensional monoatomic lattice. Okay, this is one dimensional monoatomic lattice, and we'll study their vibration and then the frequency of the vibration. Okay, very important. So so it seems that it looks like that these are attached with spring of whose spring constant is c. Okay, So from here we'll get that frequency of the vibration, that is of frequency, angular frequency. Okay, the angular frequency is 2c upon m, 2c upon m into 1 minus cos k. Very important formula, guys, you need to note down. Okay, this is the angular frequency of the vibrations, lattice vibrations in 1D. Okay, okay, so that's what we are studying, one dimensional monoatomic lattice. This is their vibration. Okay, so this is very important. So this is the angular frequency of one dimensional monoatomic lattice vibration. Okay, this is the angular frequency, and from here we can simplify it further. So this is going to be omega square 2c upon m, and this is going to be 1 minus cos k. We'll use trigonometric identity. So this is going to be 2 sine square ka by 2, right? And from here 1 will get cancelled, and minus minus plus, so this is going to be 4c upon m sine k by 2. This is the angular frequency, guys, omega square, right? So from this is very important. So angular frequency, this is going to be, then omega value is going to be very important, under root 4c upon m, under root 4c upon m, this is sine square. Okay, 4c upon m sine k by 2. Very important formula, you need to note down and memorize it, guys. Okay, we'll solve the question using this formula. Okay, so this is the angular frequency of lattice vibration in one dimension. Okay, well, this is the angular frequency, omega. Okay, well, now, and this is also known as dispersion relation for one dimensional monoatomic lattice. Okay, so dispersion relation, dispersion relation for one dimensional monoatomic lattice. Monoatomic lattice. Okay, so this is the dispersion relation for one dimensional monoatomic lattice. Okay, so omega equal to root 4c upon m sine k by 2. Root 4c upon m sine k by 2. Okay, very important formula. Now we'll study different cases for this frequency. Okay, so now for this we are going to study different cases. Okay, so this is first is case number 1, case 1, at low frequency. Okay, at low frequency, at low frequency. Okay, at low frequency, that is k, at low frequency oblique higher wavelength, at low frequency oblique higher wavelength. Okay, and in this case, okay, in this case k is at low frequency, k is less than 1. Why? Because at low frequency higher wavelength means we know, right, k equal to 2 pi by lambda. Higher frequency means lambda is value is very high, means this means k is going to be very less. Okay, so this is less than 1. Okay, so at low frequency, this value sin k by this at this at low frequency, right? So k value is very less, right? So k is very less. This means k upon 2 is very small. Okay, so it means sin k by 2 is going to be almost equal to k by 2. This is at low frequency. Low frequency oblique higher wavelength means, since we know this, for k equal to 2 pi by lambda, lambda is very high, so value of k is very less, very small. So in that case, sin k is almost equal to k. So in that case, that omega frequency is going to be, angular frequency omega is going to be root 4c upon m, and sin k by 2 means k by 2, right? This is almost equal to this. This is ka by 2. Okay, or 2 and 4, root 4 is value of root 4 is 2, right? 2 will get cancelled, then omega is going to be root c upon m, root c upon m ka, root c upon m ka, right? So from this we can get d omega, we can get omega upon k, we can get, I'll write in next page. So we can get vp, that is phase velocity, right? Vp, that is omega upon k. So from here you can see omega upon k is going to be, k will take this side, right? Right from this, we will write this later. This is going to be root c upon m, right? So this is going to be, from here omega upon k, k will take this side, right? So omega upon k is going to be root c upon m a, right? Root c upon m a, root c upon m a, right? And omega upon k is phase velocity, we know, right? That is vp. And similarly we'll find vg. Vg is d omega upon dk, right? So this is the omega, d omega upon dk is going to be this one, right? Root c upon k. So this is root c upon m into a. This is vg. So from these two we can see equation 1 and 2. So we can see this vg equal to vp, group velocity equal to phase velocity. Okay, and that is equal to root c upon m into a. So for 1D 1D, that is monoatomic, 1D monoatomic lattice, 1D monoatomic lattice vibration at low frequency or higher wavelength. Okay, Vg, the group velocity is going to be equal to phase velocity, and that value is root c by m. Okay, this one. Well, and all we can, this implies we can write at low frequency, at low frequency, at low frequency oblique large wavelength, the monoatomic lattice, the monoatomic lattice monoatomic lattice becomes as, at, because the group velocity is phase velocity, right? So at low frequency or large wavelength, the monoatomic lattice becomes as homogeneous. Becomes as becomes as homogeneous. Okay, homogeneous medium or non-dispersive medium. Okay, non-dispersive medium. So it becomes homogeneous medium. Okay, so the lattice monoatomic lattice becomes homogeneous or non-dispersive medium. Okay, homogeneous medium at low frequency and oblique large wavelength. Okay, now second case we are going to study, case number second. Case second is at higher frequency or low wavelength. Okay, at higher frequency, oblique low wavelength. Okay, at higher frequency, since we have omega value is root 4c upon m, very important, you need to note down this angular frequency. Okay, 4c upon m sine k by 2, 4c upon m sine k by 2, right? 4c upon m sine k by 2. Okay, so this is going to be so now Vp is going to be omega upon k. Omega value is this, right? So Vp, because at low frequency, at higher frequency, because we have value of omega is this, guys, this, right? So this is omega upon k, means 1 upon k root 4c upon m sine k. This is at higher frequency or low wavelength. Okay, because we know k is 2 pi by lambda. Low lambda means k is greater. Okay, lambda decreasing means k is increasing, and from here also we can find this, the value of k, right? And since this one k ka by 2 is equal to plus minus pi by 2, so means from here value of k is plus minus pi by a. This is the boundary for the first Brima zone, pi by a. K value is plus minus pi by a. Okay, k value is plus minus pi by a. Okay, so this is the Vp, guys, and Vg is going to be d omega upon dk, right? So we'll differentiate it. So this is going to be root 4c upon m into this is a by 2, and sine differentiation from sine is cos k by 2. So this is the value of group velocity. You can see both values are different. Okay, so now, and so we can see at higher frequency Vg not equal to Vp. So lattice vibration is that is this one. At low frequency the monoatomic lattice becomes homogeneous medium. So here at higher frequency the monoatomic lattice is non-homogeneous medium or dispersive medium. Okay, this Vg equal to not Vg not equal to Vp. Okay, and value of k is boundary. These are the boundaries of first Brima zone. Okay, plus minus pi by a. K equal to plus minus pi by a. K by 2 equal to plus minus pi by 2. So k equal to plus minus pi by a. Okay, so this is important. Now case third. Case third. Case third. Case third. In case third, you can see if lambda tends to infinity. Lambda tends to infinity means k value is going to be 0, right? Because 2 pi, k is 2 pi by lambda, right? K is 2 pi by lambda. If lambda tends to 0, infinity means 1 upon infinity is 0, right? So value of k is 0. So in that case, Sine k by 2 is going to be sine 0, right? K value is 0, that is 0. So in that case, this one Vp is going to be this one. Vp value is this, right? 1 upon k root 4c upon m, right? Vp. So this is 0, right? So Vp is going to be 0. Sine 0 is 0. So Vp, value of Vp is going to be 0. Okay, because sine 0 is 0, right? So this is the value, and Vp is going to 1 upon k root 4c upon m, and sine 0 is 0. So that's why Vp value is 0 for third case, that is when lambda tends to infinity. Okay, similarly we can find value of Vg, and Vg is going to be in this case Vg k equal to 0, right? So here this is Vg, right? So this k 0, k cos 0 is 1, right? So this is going to be a by 2 root 4 c upon m, right? So Vg is going to be a by 2 root 4 c upon m. Okay, so these are the three different conditions for this one, for angular frequency, that is root 4c upon m, okay, sine k by 2, right? This is the angular frequency, very important, guys. So we have studied three different cases of omega, right? Next is, so I'll show you the diagram. Okay, diagram. So this is very important diagram for 1D monoatomic lattice, okay, which you need to know. So there's a diagram. Okay, so this is like this. And this one. This one, okay. This one. This is the graph between omega, angular frequency, versus k, wave vector, okay, for 1D monoatomic lattice, and this is going to be like this. Okay, this is like this. This one, okay. So this is Vg, and this value is 0, guys. Okay, Vg value is 0, and Vp, this is Vp, and this value is 1 upon k for higher frequency, guys. This one, right? Case 2, Vp equal to this, and Vg equal to 0. Why? I'll tell you. This one, 1 upon k root 1 upon k root 4c upon m, 4c upon m, okay, 4c upon m, and this is the omega c value, okay, and omega c value is, this is equal to root 4c upon m. Important value, guys, omega c. This you need to know, okay, omega c value, and this is minus pi by a, and this is pi by a, okay, and this total distance is from here to here 2 pi by a, 2 pi by a, 2 pi by a. Okay, this one, this is minus pi by a, this is pi by a, and this is omega c, this is root 4c upon m. Okay, root 4c upon m, this value, and this is pi by a, and this is omega versus k. Okay, so this distance is 2 pi by a. Okay, well, and at pi by a, this value Vg is going to be cos pi by a, means this in place of k will write pi by a. Pi by a means a get के pi by 2, right? Pi by 2 value is 0. Cos pi by 2 is 0. Sin pi by 2, pi by a, if you put k equal to pi by a will get cancelled, and sin pi by 2 is 1, right? So that's why this value is 1 upon k root 4 c upon m. Okay, so this is very important graph, and this is the graph of wave vector versus angular frequency in 1D monoatomic lattice. Okay, 1D monoatomic lattice vibration. Okay, so this is the graph, and at this value Vg is equal to 0, Vp is 1 upon a root 4c upon m, and omega c value, critical frequency, right? Omega c value is root 4c upon m. Okay, and there is one more point, and that is 1D monoatomic lattice. 1D monoatomic 1D monoatomic lattice. 1D monoatomic lattice behaves as low pass filter. Okay, low pass filter, that is LP. Okay, well guys, so this is about 1D monoatomic lattice. Okay, so what you need, which is important thing here, you need to know this diagram, very important. It may be asked in the question, okay, in the examination. So this graph is very important, omega versus k, and this value you must know, that is omega c. At higher frequency, these are the value, and this is the graph where the boundaries are minus pi by a, and pi by a, right? So at pi by a, the value of at higher frequency, omega value is going to be, this value is 1, right? So this value is going to be 1 upon k root 4c upon n, right? And Vg value is going to be 0, because if you put k equal to pi by a in this equation, or minus pi by a in Vg here, right? Cos pi by it is going to be cos pi by 2, cos 90 is 0, right? 0, right? So this value is 0. And omega c, the critical angular frequency value is 4c upon m. And in 1D monoatomic lattice vibration, this is very important formula which you need to note down, right? And you need to memorize it. This omega equal to root 4c upon m sin ka by 2. And if you know this, these are 3 different cases, guys. First case is this, at low frequency. Okay, at low frequency, because k value is going to be very less, means sin k value is very small, right? Since sin k by 2 is almost going to be k by 2, then we can get the value of omega. Second is, if at higher frequency will find group velocity and phase velocity, right? And they are not equal, and value of k is that boundary condition, that is pi by plus minus pi by 8. Okay, yeah, this is what you need to note down and memorize it, guys. Okay, so if you know these things, you can easily, and this is also called dispersion relation for one-dimensional monoatomic lattice. Okay, this is also dispersion relation, very important, and you will get many questions, okay, from here. Okay, and you can use this formula and easily solve those questions. Okay, and this is the one-dimensional monoatomic lattice vibration. Okay, and these work as a spring, and and spring constant is c, we have taken. Okay, and this is the acceleration we know, right? That is m. This is the simple harmonic equation, and this is the restoring force. Okay, so this is very important, guys. You need to note down, and and solve questions related to it using these formula, guys, right? In next lecture we are going to study this one, that two-dimensional that one-dimensional diatomic lattice vibration, lattice vibration we will study. Okay. Well, guys, I'm going to stop here, and also I would request the students who haven't subscribed my channel yet, please subscribe my channel and watch my free live lectures, which are going to help you to crack the exams related to physics, physical science. Okay. Next lecture is going to be electronics lecture, guys. Okay. Okay, guys. Thank you so much. Bye now.